In this video, we're going to talk about correlations and the correlation coefficient. A correlation is nothing more than a relationship between two variables. But what we're going to be focusing on in this lecture is the linear relationship between two numerical variables or two quantitative variables. There are other types of correlation coefficients for different other types of variables. What we're going to focus on in this lecture is on two quantitative variables. Well, since we have two numerical or quantitative variables, we can think of our data as a set of ordered pairs, x comma y, where x is the independent variable. A lot of times we'll say that x is the predictor, and then y is our dependent variable. Some people call it the criterion variable or the predicted variable. To help us explore the relationship between x and y, or the predictor and the criterion variables, we can construct a scatter plot, which is basically a graphical representation of that relationship. And it's basically your plot of ordered pairs. And so I have an example here where our variable x is the amount of community service hours individuals in a study has completed, and y is the happiness score on an assessment that measures happiness, and that scale is on a scale that score is on a scale between 0 and 20. Remember back in algebra, when you started graphing points or plotting points in the Cartesian coordinate plane, you will always start at the origin, and your x tells you how far to the right or left from that origin to go to get to your ordered pair, that the point that was represented by your ordered pair, and y represents how far up or down from the x-axis to go and plot your ordered pair. And so I've graphed this scatter plot using JASP, which I'll show you in a little bit. But I just wanted you to see, again, that we're using the same methods to graph ordered pairs as you're accustomed to. So for instance, I can look at these points. If I start at 0 and go to the right to 14.4 and go up 14.7, I will get to this point here. So this point here represents that a person who volunteers for 14.4 hours has scored 14.7 on the happiness assessment, or whatever that battery is used to measure happiness. Another point, this indicates that this person volunteered for 6.5 hours and their happiness score was 12, right? And so with those points being plotted, we can now kind of see that we kind of get a relationship between those two variables by looking at patterns. And so let's talk about those types of patterns when we're talking about correlations, focusing on linear relationships. One of the types of correlations is going to be a positive correlation. As you can see from this graphic here, as x increases, now we always read graphs from left to right. That means if I start at the origin and I go to the right, so from left to right, that's as x increases. This horizontal is our axis, is our x-axis. We always read graphs from left to right. So we always say as x increases. We want to see what the y values are generally doing, and our y values are referencing this vertical axis. Well, if you look, our y values from left to right are tending to go upward, and so we say y tends to increase. Anytime this happens, we call this a positive correlation. We have, in general, the opposite scenario in this example. That means we have a negative correlation. As x increases, or from left to right on that graph, the y values are tending to get smaller. And so we'll say that y tends to decrease when we have a negative correlation. There are times where we may not see a slanted linear relationship, right? So in this case, we have a very weak to no correlation here. That means as x increases, y kind of varies randomly. We can't say that y generally increases or y generally decreases. It's kind of like a straight pattern of random points from left to right without an increase or decrease. We call that a weak to no correlation. There are other correlations that we're not going to be focusing on. And this example, this last graph is an example of that. This is a non-linear relationship, right? As X increases, Y kind of varies. Y at some point increase and that Y values sometimes decrease, right? This is a non-linear correlation. So that means there is no linear relationship. Our methods that we're going to be focusing on in our course are not going to be able to um, we're not going to be focused on relationships like that. We're not going to be able to apply our methods when we see a pattern like that. So the types of correlations we'll focus on are those positive linear, negative linear, are those weak or no correlations. So let's see how we can create a scatter plot and then use that scatter plot to identify the actual relationship in our data. And so I'm going to open JASP, and for our correlation example, I'm going to open it on my computer. I have some correlation data here. I'm going to start with these two columns here. So for this part of the lecture, I'm going to use these two variables here, community service hours, and then happiness score. All right. If I want to create a scatter plot, I'm going to go to descriptive statistics. I'm going to put the variable that I want on my x-axis first. So I'm going to put just for, well, we identified community service hours as X. So I'm going to put community service hours first and then happiness score second. Notice it gives me some descriptive stats about that. But if I want to create a scatter plot, I'm going to go to customizable plots. Oh, I passed it. I'm going to go here to scatter plot. I want to uncheck add regression line, and I don't want a graph above the scatter plot, and I don't want a graph to the right of the scatter plot. And so here I see my scatter plot for this relationship here. And so if I go back to my notes, I can discuss that scatter plot, which is the same scatter plot that we saw on the first page. But basically, we can say that there does appear to be a positive correlation between community service hours and happiness score, because as our X values increase, meaning from left to right, our Y values are the points in that scatter plot increase. All right. Now, this is a very strong relationship, a strong positive relationship between these two variables. There are times where we may not be able to identify whether that relationship is like strongly positive or strongly negative. And so we have actually a number or a statistical index known as the correlation coefficient that we can also use to verify that we have a strong positive or a strong negative correlation coefficient. All right. And it's called your correlation coefficient. And so your correlation coefficient does two things for us. What we focused on when we talked about the positive, the negative, and the weak correlation is we talked about the direction of that correlation. But a correlation coefficient actually is a measure of the strength and the direction of a linear relationship between two variables. All right. The correlation coefficient that we're going to be focusing on, there are multiple correlation coefficients, but we're going to be focused on the Pearson product moment correlation coefficient. Pearson product moment correlation coefficient. A lot of people abbreviate it by saying Pearson's correlation coefficient or Pearson's R. The variable that we use for a correlation coefficient is R. This is the formula for Pearson's correlation coefficient. We do 1 over n minus 1, and we do the sum from I equals 1 to n. Here, n is the number of pairs, right? I do x sub I minus x bar over the standard deviation of the x variable, and I multiply that by the same thing in reference to my y variable. Now, if you look at this says go to every observation x, subtract the sample mean, and divide by the sample standard deviation. That should sound very familiar to you. It is nothing more than a z-score. right? So we can think of Pearson's R, our correlation coefficient, as the sum of the product of the z-scores for every point in our data set, and then we divide that by n minus 1. All right, that's one way that we can think about that. All right, but it's a measure of the strength and the direction of that linear relationship. And so let's talk a little bit more about matching the correlation coefficient values to actual what we may see in scatter plots, right? So the correlation coefficient is going to range in value from -1 to +1. All right. If it equals -1, then there's a perfect linear negative correlation, right? That means if it's perfect, that means all of the points on that scatter plot are going to lie on the line and it's going to have a negative slope, right? And so an example of a data set where the correlation coefficient equals -1 is shown here. All of those points are on the line, and that line has a negative slope. One of the things that I don't want you to confuse is the correlation coefficient R with the slope. It doesn't mean that the slope of that line is -1. It just means that all the points on that line are in that scatter plot lie on that line. It can have any negative slope. All right. The opposite happens for R equals 1. When R equals 1, there is a perfect positive correlation, right? That's the strongest correlation we'll ever see. And so that's a perfect positive correlation. All of the points are on a line with a positive slope. All right. The closer the value of R is to either 1 or -1, the stronger the relationship is, whether it's positive or negative. The closest it is to 1 or -1, the stronger the relationship, right? And by strength, I means the closer it approximates a line. So there's not going to be as much scatter about the line the closer that value of R gets to 1 and -1. The closer it gets to 0, the weaker that relationship is. And that means there's going to be a lot wider of a spread or scatter in that scatter plot, right? Because if R is close to 0 or equals 0, then there is no linear relationship, right? Or weak to no linear relationship. And so we're going to see that random scatter. And so the closer we are to -1, the closer it approximates a line. The closer we are to 1, the closer it approximates a line. The closer it is to 0, the more scatter and further the data deviate from a line. All right. Now, we're going to have sample data, so we'll probably not see a correlation equal to -1 and +1. In fact, most of the times we don't, right? So I just want you to see some examples of what some strong correlations may look like, as well as some weak correlations. So for instance, in this example here, we have a strong negative correlation coefficient, right? Those points aren't on a line, but they're pretty close together. That's a very, very, very strong correlation there. All right. So we have a strong negative correlation. Even when we get to the R equals 0.88 here, notice those points are not on the line, but they're pretty linear. And so this is also a strong but positive correlation here. Usually, once you get to about zero point 0.7, that's when we say in the social sciences, we have a pretty strong correlation. So it's going to be greater than zero point 0.7 or smaller than -0.7. zero point 0.7. That usually indicates a strong correlation. Now, you'll see examples like this where the correlation is around 0.4. This is a weak getting to moderate. I think about 0.4, we start to say maybe it's getting to about 0.4, 0.5 being moderate. I would call this a weak to moderate positive correlation. And of course, if there's just a bunch of scatter, we'll say that there's a weak or no correlation, right? I would use weak to no correlation for this example. I don't say weak on the slide here, but I say weak to no. All right. So 0.7 or higher or smaller than -0.7, we're going to say strong. Once it gets to point 4 um, or below, we're starting to say weak. Now, that's what happens when we look at a scatter plot, right? And the correlation coefficient is our sample correlation coefficient, right? So when we collect the sample, we measure the individuals on X and Y. When we calculate that sample correlation coefficient, that represents what happens in our sample. But usually, we want to draw conclusions about the population. And so we have another symbol. It looks like a italicized P here, but it's a Greek letter rho, R-H-O. This represents our population correlation coefficient. All right. It still ranges in value between -1 and 1, where if it's -1 or 1, it's a strong positive or a strong negative, perfect correlation. The closer it is to 1, the closer it is to -1, the stronger that correlation is in the population. The closer it is to 0, the weaker it is, right? So all of that stuff still applies to the population correlation coefficient, but now we'll be speaking about the population instead of the sample. Of course, we don't know this value. Usually, we can construct a confidence interval and do a hypothesis test to get some information about some potential values for that population correlation coefficient rho. And so, if we wanted to conduct a hypothesis test, our null hypothesis is that our population correlation coefficient equals 0. And then, of course, the population correlation coefficient can be positive, negative, or not equal to 0. So we have several alternative hypotheses here that can be both directional or non-directional. We can choose. If we choose a non-directional, so we use rho not equaling to 0, that means our variables are correlated as our alternative hypothesis. If we just want to know if they're related or correlated. If we want to know if they're positively correlated, we can use that second alternative hypothesis. And if we want to know if our variables are negatively correlated, we can use that third alternative hypothesis. All right. In JASP, we're going to use the regression tool in JASP, and there's a correlation module or menu within that regression module in JASP. And so what we're going to do is we're going to run to this example here. It says another researcher interested in investigating the relationship between hours of community service completed by students with previous disciplinary actions and their corresponding self-reported happiness scores on a scale of 0 to 20, conducted a study with a sample size of 20. So this is going to be slightly different from the previous example. We're going to create a scatter plot. We're going to find the value of R, interpret the value of R, and test whether the population correlation coefficient is greater than 0. Let's go to JASP. So this was the example, our last example. I am going to not use that one. But in that same data set, I have the sample of size 20 in the third and fourth column here. And it's community service hours 1 and happiness score 1. All right. I'm going to create a scatter plot first, going through that same process as I did before. So I'll go to descriptives here. I want community service hours on my X, so I'm going to put that first. Happiness score second. I'm going to go to customizable plots. I'm going to do a scatter plot. I don't want the graph above the scatter plot. I don't want the graph to the right of the scatter plot. And I don't want to add a regression line. And so here I have my scatter plot. To me, this looks like a positive, strong correlation, right? We can verify that by calculating our value of R. And if it's greater than 0.7, I'm going to have some evidence that in my sample, at least, we have a strong positive correlation coefficient. All right. So one of the things we want to do is create that scatter plot. I have that. Now I want to find the value of R. So to do that, I'm not going to use the descriptives menu anymore. That gives me my scatter plot. I'm going to go to the regression module here. And the first option under classical is correlation. So I'm going to click on correlation. Again, I'm going to put my variables here. All right. Now, I will tell you in this menu, the order in which you put these does not matter. All right. But if I look at what popped up, this is a correlation matrix. There are times when we have studies with multiple variables, more than two variables. We're only looking at two right now. And sometimes we want to know the combination of correlations between those variables, right? And so a correlation matrix allows you to easily see that. Since we only have two variables here, in this additional options, I'm going to click display pairwise, display pairwise. And that way I can see my Pearson's correlation coefficient instead of looking at a matrix. Now, remember I said the order in which you entered these does not matter. All right. If I switch my order here and put happiness first, now happiness is first. Notice I got that same value of my correlation coefficient and the same p-value. I'm going to put it back in the opposite direction. The only thing changed here was the order in which I entered that. The reason for that, right? Correlation does not take order into consideration. If you go back to this formula that we use for the correlation coefficient, it's the sum of the product of these z-scores here, right? Well, multiplication has the commutative property, which means that the order in which you multiply things does not matter, right? And so whether I do z first and x second, or x first and y second, I know I put z in there. The order doesn't matter because we're multiplying in order to get those values. And so correlation doesn't take directionality into consideration. I just wanted to point that out. Now, this gives me the results of my hypothesis test. I will let you know that if you do want a correlation coefficient, a confidence interval, you can select confidence interval here. But this problem did not ask for the confidence interval. But one of the things that I want to do here is review what our null hypothesis was, right? In the problem, it requested that we test whether the population correlation coefficient is greater than 0. All right. So that means that the correlation is going to be, the variables are going to be positively correlated. All right. And so I'm going to have this here. And so that is all I need. I get the results from and notice here, this is such a strong correlation that these values are extremely significant. So nothing changed when I changed it to a one-tailed test compared to when I had it as a two-tailed test. And so this is a very significant test for a positive correlation. All right. And so if I want to interpret my results, that is all we need from JASP. Because our R value, well, let's start with the scatter plot. We already said this, but the scatter plot shows that we have a positive correlation in the sample. Our correlation coefficient R tells us that we have a strong positive linear relationship or correlation between these two variables because this value is larger than 0.7. And by testing this null and alternative hypothesis, we obtain this p-value here, which means that we do have sufficient evidence to conclude that community service hours worked and happiness score are positively correlated. There's enough evidence, right? We rejected the null since our p-value is less than alpha. So we can expect in the population that relationship is a positive linear relationship. All right. Now, one of the things that we always have to remember, especially when we do studies concerning or involving the correlation coefficient, and it has to do with causation. The fact that two variables are strongly correlated does not in itself imply a cause and effect relationship between the two variables, right? So even if we get a very, very, very strong significant correlation coefficient, it does not mean that the x variable causes a change in y. there has to be some very, very important features of the study that take place in order for us to use causal language. And in observational studies, we don't have that. We need some experimental studies to do that. But these are a couple of reasons why we can't say that our causes our Y to behave in a certain way. One is the directionality, and it's something that I pointed out when we looked at that formula. Um, we can't say that there is a direct cause and effect relationship in between those variables because we don't know, our correlation coefficient doesn't test the directionality. We can't say that X causes Y because we don't know whether X caused Y or Y caused a change in X, right? That directionality was not tested when we did these tests for the correlation coefficient. Also, because we haven't set up an experiment, there could be alternate explanations. So there could be a possible third variable that can be explaining the relationship between those two variables, or there may be a third variable that's acting on each of those variables or one of those variables that cause the strong correlation that we may see in our data. Another thing that I want to point out is that when we see a significant correlation from the hypothesis test, it doesn't necessarily indicate that that is going to be a strong correlation. The reason why I can kind of be a little confident, or one way that I can be confident that we're going to have a very strong positive correlation, is if I do a two-sided confidence interval. I'm going to go back here to select alternative hypothesis correlated, and then I'm going to get a confidence interval. This tells me that my confidence interval, I expect in my population, my correlation coefficient to be approximately from between 0.708 and 0.95, and that covers the strong values of a correlation coefficient. But this p-value in and of itself doesn't indicate strength. The confidence interval can help us talk about our population correlation coefficient potentially being strong. All right. But that's our introduction to correlation coefficients. Next, we're going to move to studying regression. And so I'll see you in the next video.